Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 45. We are in chapter 13. This is part 1. In the previous chapter, chapter 12, we talked about dummy variables or indicator variables, how most of us refer to them. We gave the rules for defining dummy variables, how to compare two straight line regression equations, questions for comparing those two straight lines. Those included are the lines parallel? Do they have the same intercept? And are they coincident? In other words, are they identical? Same slope and same intercept. Okay. We talked about two different methods for comparing straight lines and showed that method 1 had a lower power, so we don't use that. We use method 2. And in method 2, we showed how to test for parallelism, equal variances, or equal intercepts, and both parallelism and equal intercepts or coincidence. We talked about some strategies and interpretation comparing two straight lines and went over some examples. All right. So in chapter 13, we're going to talk about something called ANACOVA or ANCOVA. We'll give a brief overview, talk about an adjustment problem, analysis of covariance, the assumption of parallelism, and then we'll talk about ANACOVA for several groups and several covariants and give some examples. So let's get started. So this is a preview. So among predictor or independent variables, some are considered to be major contributors and some are considered to be concomitant. And so major contributors, another name for these are study factors and another name are exposure variables. Now, in this situation, let's say we had a test for pain that was being done. And so drug 1, drug 2, and the placebo, that would be a major contributor to the study for pain, right? Because those should definitely impact whether the pain is abated or not. Then for concomitant variables, we could also call them control variables, covariates, secondary variables, subordinate variables, incidental variables. So quite a few names for the same thing. And again, for the pain, while we have the major variables or the study factors here, we could have control variables such as systolic blood pressure and gender. Okay. So analysis of covariance is used to study the factors when the study factors are treated as, or they actually are, nominal variables to adjust for the covariance. And so we're going to use dummy variables or indicator variables when we have nominal variables. So ANACOVA, we're going to assume that there's no interaction between the covariates or concomitant, not non, concomitant variables, okay, and with the study or major variables. But we will need to test for this. So this is something that we will have difficulty analyzing it if the interaction is present, but we can handle it, but we need to test and make sure, before we ignore it, we need to make sure that it is in fact not present. Okay, so the most common use of ANACOVA is something called an adjustment problem. So if you recall back in chapter 12, we used the age and systolic blood pressure data for males and females and checked if there was any significant difference between the slopes of males and females, and there wasn't. Okay. So the model we used was given here with X, Z, and XZ, and Y is SBP, or systolic blood pressure, X is age, and Z is gender. Okay. We checked the parallelism by testing that beta 3 is equal to 0, but we could not reject H naught. So we then checked if they were coincident by using beta 1 plus, or beta 2 equals beta 3 equals 0. And of course, if they were coincident, then we would have this as our equation. Okay, but that was not in this case. We did not. Okay, so the goal here is to report the average value of response after adjusting for a control variable. Okay, so after adjusting for a control variable. So let's take this example. It may be that males are older than females on average, or older than the average age. So here, this could be the overall average between males and females. And you'll see that up here is where we see the males falling. And then females are falling way down here. So between the two of them, the average is in the middle, but the males overall are older and the females are younger. Okay, so we need to control for that age difference. Okay, we want to check, in this chapter, we're going to check whether the mean blood pressure levels for male and female groups differ significantly after adjusting for the possible difference in age between the two groups, as we just mentioned. Now, we're going to fit the regression model, y equals beta naught, beta 1x plus beta 2z plus epsilon. No interaction again, okay? So x is our control variable. It's continuous, okay? So the covariates are continuous. And the major contributor is nominal. Okay, or we're using an indicator variable for that. Again, this model assumes no interaction, so let's revisit our test of parallelism. And so we're going to test h naught beta 3 equals 0 versus h naught beta 3 not equal to 0 in the model with the interaction. Okay, and we have our two lines for when it's male and female. For male, z is 0, so the equation reduces to this. And when female, the z is 1, so we end up with a, I call it a compound intercept, because we're using two intercepts get added together, and a compound, if you will, slope or coefficient for the age here. Okay. So our test statistic, if you remember, was a partial F test, testing whether xz is significant in the model or not. And so we are going to look at xz given x individually and z individually. Now, the book again does a nice convoluted calculation based on having different ANACOVA tables or using the SSR, but it's easy enough to just get the 0.5494 from the table as well. But you could calculate it with SSR of all three minus SSR of just x and z over the MSE of all three, the full model. And we get an F value that's very small, so 0.007. And this has a degree of freedom of 1 in 65. Okay, so it shows the calculation here, 3 minus 2, and that's just 1. The difference between the two models is just 1 degree of freedom in the numerator, and the MSE, if we look up here, has a degrees of freedom of 65. Okay, so the p-value is very large, so we do not reject h naught that beta 3 is 0. So we can use this model. So we've just verified that we don't have interaction in the model. Okay, so we can use this model, and as it says here, that's justified by this test. Now, from the least squares fitting line, we have these two equations. Okay, because beta 3 now, we're saying that beta 3 equals 0. Okay, we could not reject our null hypothesis that beta 3 is 0, so we're going to set beta 3 equal to 0, and it's not in this equation anymore, okay, or this one. So this is our new equation for females without beta 3. So it says, note that the adjusted mean scores are computed as if both male and female groups have the same age distribution. By doing so, we can adjust for the possible difference in age distributions in the two groups. So this is the coefficient for the dummy variable, beta hat 2. And so we can take that as, if you look at these two equations, if we subtract them and solve for beta 2. So that's what we're doing here. We're going to say let's subtract these two equations. I'm going to take y bar f adjusted minus y bar m adjusted, and that's going to equal beta naught plus beta 2 plus beta 1 hat x bar, these are all hats, minus beta naught plus beta 1 x. And this is going to equal this, and this will cancel out, and we are left with, let's see, we've got beta 1 hat minus beta 1 hat. So we are left with, so this cancels out, oh, not that one, I'm sorry. So this cancels out with this. And so we're left with beta hat 2 is equal to y bar f adjusted minus y bar m adjusted. Okay? And they've done that down here, and I've shown that the only thing that we have left is beta hat 2. Okay. So here are our lines that we have. So the adjusted line is beta naught plus beta 1 hat x bar, and then so that this goes across for the males, right? Y bar adjusted is that level, so this value, and then y bar f adjusted is going to be this level, and we see our lines over here. Okay. So let's do an example. From the least squares fitting, we have that y hat is equal to 110.29 plus 0.96x minus 1351z. Let's see where we got those. So we've got them from right here. This is beta naught, beta 1, and beta 2. Okay? And remember that this is, we're not using that. We're saying that that's too close to 0, and we're ignoring it or leaving it out of the model after our test. So we use those coefficients and plug into our equation to get this line for y hat. Okay. So when z equals 0 now, then this goes away and we're left with this. When z equals 1, this term with z in it just becomes the negative 1351. We add that to 110 and we get the same slope but 96.78. Okay. So the adjusted mean scores from these equations are given by plugging in the mean, and this value was given in the book. So we're plugging in the mean value for x bar. Okay, so x bar here. So we're plugging in, we get 4614 there, and the total is 154. So the adjusted mean scores 154.58. and 141.07. Now remember that Y is our systolic blood pressure. So the males on average have a higher mean systolic blood pressure after controlling for age. Okay? And so here are our a summary. So for the unadjusted, we still have that they are higher than the females, but you'll notice by adjusting for age that they become closer to each other. So the difference of the adjusted mean scores are smaller than the difference of the unadjusted ones, and that's because the mean age for males is 46.3, while the mean age for females is 45.07. And by using this 46.14, the adjusted mean score for males gets smaller, and the adjusted mean score for females gets larger. So we can perform the test H naught beta 2 equals 0 to see if the two adjusted scores are significantly different. Okay? So we have a reduced model with beta 2 equals 0, and we're given the sum of squares regression and the sum of squares residual or error, and then the model, the complete model, and this has x and z in it in this case, but not xz, no xz term. Okay? So the sum of squares for xz has been added back into the SSE here from above. All right, so we have 5201 for the sum of squares error and 180978. And we've seen this data before back in chapter 12 when we were looking at this example as well. Okay. So our F statistic for testing H naught beta 2 equals 0 versus HA beta 2 not equal to 0 in the model y equals beta naught plus beta 1x plus beta 2z plus epsilon. Okay. So we're going to use this partial F test, z given x, so variables added in order. And we have SS of z given x, and again, we're going from 2 to 1. So 2 here and 1, so 2 here, 1 here. And so the difference, the additional number of variables is 1, so we're dividing by 1. Okay? And then we're using the MSE of both x and z. So here, we'd have to take these two values and subtract them. And then we could use the MSE for the full or complete model in this case. And so we have this, and we get an F statistic of 38.8, and it has a degrees of freedom of 1 and 66. Okay, so notice here we had a degrees of freedom of 67. Here we have 66. Okay, the p-value is less than 0.001, so we're going to reject H naught that beta 2 is equal to 0. So we're saying that the two adjusted scores are significantly different. So there does exist sufficient evidence to support the claim that the two adjusted scores are significantly different or beta 2 equals not equals 0 at a, we could just say 99.9% confidence level. We could use the largest one available. We said it's less than 0.001. Tested with a simple random sample of n equals, it looks like 68 or 69. Let's see what we have up here for the total. Oops, there it is. 69. Okay. Okay. Because the analysis of covariance model assumes parallelism, we need to test if we can remove the interaction terms prior to ANACOVA. In the example, in the above example, we've checked that beta 3 is equal to 0, and the result was that we did not reject this. So the assumption of parallelism was justified, right? If the test shows that the assumption of parallelism is not justifiable, then we should not seek an adjustment. So please remember this fact. So we should not use this method of adjusting when we have interaction. So that's good to know. Now, when we have several groups and several covariants, in general, ANACOVA can have K groups for the study factor and P covariates. So K, these are the major contributors, and these are the covariants or concomitant variables, okay, to be adjusted. And the regression model will be written something like this. We have x1, x2 up to xp, and then we have z1 up to zk minus 1, okay? But notice that beta 1 up to beta p, and then beta p plus 1, all the way up to beta p plus k minus 1. So k minus 1 plus, p here. K minus 1 plus p. Well, actually, I should circle this one. And so that's giving us this k plus, or p plus k minus 1. And z sub j equals 1 if we're in group j, and 0 otherwise. And j goes from 1 to k minus 1. Okay? And then our y-adjusted j is beta naught plus beta hat p plus j. So this corresponds to z sub j, right? Because z sub j would be some value between z1 up to zj up to zk minus 1. And it could be z1, it could be zk minus 1, but it's just some j, but where j is between 1 and k minus 1, j in natural numbers or integers. Okay, it's positive integers. Okay, so then we have, so that would be combined, because in this case, z sub j would equal 1, and all of the other z's would be 0. Because we're not in their group. We're just in the jth group. Okay? And so all that we'd have left are these first, yeah, not there. We'd have these first, yeah, here we go. Right here. We'd have these variables left, and that's what we have here. Okay? And again, j equals 1 up to k minus 1. So then we have y bar k, so this is adjusted for k, the kth group, and if k, notice we have k minus 1, so if we have k, then all the z's are 0, okay? And so we're left with the equation without any of the control variables in it, just beta naught hat plus beta 1 hat, x bar 1, all the way up to x bar p. Okay. To test if the k-adjusted mean scores are the same, we test that beta p plus 1 equals beta p plus 2 up to beta p plus k minus 1 and equals 0, that they're all equal to 0. So all of the coefficients for the z's are equal to 0, these here. Okay. So that's how we test if they were the same. And we use a multiple partial f-test. Okay. And we'll have k minus 1. For the k groups, we need k minus 1 dummy variables. So we have k minus 1 dummy variables. And then we'll have n minus p minus k degrees of freedom. And so remember that instead of n minus p minus k minus 1, right, that we have to add back beta naught. So we're going to have p variables here. We're going to have k minus 1 variables there, and then we're going to have one more for this. So we end up with p plus k, not p plus k minus 1. Okay, that's a better explanation than this one. Okay, so these are our degrees of freedom. K minus 1, n minus p minus k. Okay, so that's something good to know as well. So we'll pick up here in the next video. Please don't forget to scan your lecture notes by midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't make it to virtual office hours before you need help, then by all means, email me. But I need you to email me a picture of the problem and a picture of your work so far so I can see how you are approaching the problem. And I may not have the problem available, so I don't have them memorized. So please send me a picture of that as well. Please take care of yourself, and we hope to see you next time.